champs of Examsnet, welcome to the question series of Examsnet. I hope this series of detailed explanation is helping you a lot. So in today's session, we are going to discuss chemistry portion of NEET 2016 paper phase 2 and we have 45 questions here. So let's start the session. The first question is from the chapter amines and the question is a given nitrogen containing aromatic compound A reacts with SN and HCl followed by nitrous acid to give an unstable compound B. B on treatment with phenol forms a beautiful colored compound C with the molecular formula C12H10N2O. The structure of the compound A is, okay. So we have to identify the starting compound A. So it is given in the question that we have a compound A, but we don't know what is that compound. So let's make some space for the compound that will eventually identify, okay. Then this compound A reacts with SN and HCl. SN, HCl, that means reduction is being done, okay. Then something will be formed here and that intermediate that is formed after this reaction will again undergo reaction with nitrous acid HNO2 to give an unstable compound B, okay. Then an unstable compound B will be formed. Now what is that unstable compound which is formed on reaction with nitrous acid? It is nothing but diazonium salt, right? We know that diazonium salt is formed by the reaction with nitrous acid, okay. So it will be a diazonium salt. Let's draw the structure here. We have one benzene ring and here we have N2 plus Cl minus. And how is this diazonium salt formed? We know that it is formed by the reaction of a primary amine with nitrous acid, right? That means this compound, this intermediate compound should be a primary amine, and since it is given that the compound was aromatic, so this primary amine will be the aniline, okay. So this compound will be aniline, NH3 here. So it is clear that aniline on reaction with HNO2, that is nitrous acid, will form the diazonium salt. Now what is the compound A? So we know that aniline will be formed after the reduction of nitro compound, okay. So it will be a nitro compound, that means nitrobenzene. So we have identified that the correct answer will be option number C. But still, let's read the complete question. It is also given that B on treatment with phenol, that means this B, diazonium salt, on treatment with phenol forms a beautifully colored compound C, okay. So let's see what happens when this diazonium salt reacts with phenol, okay. So phenol, we have this benzene ring and here we have OH. So the reaction that will take here is known as coupling reaction, okay. Coupling reaction will take place and the resulting product will be, this is OH phenol part and here nitrogen nitrogen double bond and this side we have a benzene ring again, okay. It will be a benzene ring. So these two will be coupled together, okay, and this is the colored compound that the question is mentioning, okay. Its formula is C12H10N2O, okay. But we had to identify the compound A, so that is none other than nitrobenzene. Therefore option C is the correct answer. Now question number 2 is from the chapter haloalkanes and haloarenes and the question is consider the reaction. This reaction will be fastest in. So we have to identify the correct solvent or the medium for this reaction, right? Options are water, ethanol, methanol and N-dimethyl formamide, that is DMF. Okay, so what is happening here? Initially we have an alkyl halide, right? Alkyl bromide. And which type of alkyl halide? A primary alkyl halide. Okay, primary alkyl halide is present and it is reacting with NaCN, and as a result you can see that this CN has replaced the bromine from here, right? That means substitution reaction is taking place. Substitution reaction is taking place. And what type of substitution reaction? We know that primary alkyl halides undergo SN2 reaction, okay. SN2 reaction easily. And we know that the solvents which are most suitable for SN2 reaction are polar aprotic solvents. Okay, polar aprotic solvents are the most suitable for SN2 mechanism. Okay, and what are the examples of polar aprotic solvents? The examples are acetone, then DMF, DMSO. What is DMSO? It is dimethyl sulfoxide. Okay, so here you can see in option number D we have DMF, N-dimethyl formamide, which is a polar aprotic solvent. Therefore, this will be the correct answer. Okay, this reaction will be fastest in this medium. Whereas other three options, that means water, ethanol and methanol, are polar protic solvents, right? Protic solvents. So the correct answer for us will be option number D. Question number 3 is from the chapter hydrocarbons, and the question is the correct structure of the product A formed in the reaction. So we can see that in the reactant given here there are two double bonds, one carbon-carbon double bond and one carbon-oxygen double bond, right? And hydrogenation is being done in acidic medium. Okay, since ethanol is given, that means the medium is acidic. And the hydrogenation is done with the help of palladium and carbon. Okay, so the concept that we have to remember here is that the carbon-carbon double bond will be reduced more easily. Okay, so it will be reduced easily as compared to the carbon-oxygen double bond. Okay, in the presence of palladium and carbon. Presence of palladium and carbon. Okay, since excess hydrogen is not mentioned here, so both the double bonds will not be reduced. Suppose there had been excess of hydrogen, then what would happen? Both the double bonds would have been reduced. But since there is only limited amount of hydrogen, only 1 mole of hydrogen here, so that will be consumed in reducing the carbon-carbon double bond, and this carbon-oxygen double bond will remain as it is. Okay, so the resulting compound will be, this is the hexane part, right? And here double bond O will remain. That means the resulting compound will be cyclohexanone. So let's see which option will be the correct one. Option number C. Okay, option number C will be the correct answer. Now question number 4 is from the chapter Organic Chemistry, some basic principles and techniques. And the question is, which among the given molecules can exhibit tautomerism? Okay, so we know that in tautomerism two forms are involved. One is keto form and the other is enol form. So the thing that we have to remember here is that in keto form, suppose this is the keto form, there must be at least one alpha hydrogen. Okay, there must be at least one alpha hydrogen. Okay, so these two are alpha positions, alpha 1 and alpha 2. There will be carbons at this position, so at least one hydrogen should be attached to this position. Okay, then only tautomerism can be exhibited. Okay, this is one condition. And the second thing that we have to remember is related to bridgehead compound. Bridgehead compound. So in this type of compound, which looks like this is a 6-membered ring, and there is a bridge formation like this. Okay, so in this case what happens, if the alpha hydrogen is attached to the bridge head carbon, that means the two carbons which are involved in bridge formation, this and this carbon, if the alpha hydrogen is attached to any of these carbon, then it will not show tautomerism. Okay, so the point to remember is that alpha hydrogen at bridge head carbon will never show tautomerism. If the alpha hydrogen is present at any other position, let's say at this position or this position, then tautomerism can be exhibited. Okay, but not at bridge head carbon. So let's check. In the first option, The carbonyl part is this. Okay, this is the carbonyl part. So what are the alpha positions? These two are the alpha positions. That means the alpha hydrogen will be present at the bridge head carbon. Okay, because the carbon at these two positions are involved in the bridge formation, right? So this will not show tautomerism. Okay, not possible. You understood why? This second point. Here, the carbon that is involved in the bridge formation, this is the bridge. So the alpha hydrogen attached to that carbon will not show tautomerism. Okay. Now in the second point, we have the carbonyl group here. So what are the alpha positions? These two are the alpha position. Okay. This is alpha position 1. This is alpha position 2. Now we can see that alpha position 1, here the carbon is involved in bridge formation. So this is not possible. The hydrogen present at this position will not show tautomerism. Okay, because this is attached to the bridge head carbon. Okay, and at the second alpha position there is no alpha hydrogen. At this position there is no alpha hydrogen. So again this is not possible. Both the conditions are valid here. Okay, are, that means not valid here, these two conditions. So this is also not possible. Then in the third option, let's check. Here we have this carbonyl part. So what are the alpha position? This is one alpha position. Let's say this is alpha 1. So here again alpha hydrogen will be attached to the bridge head carbon because this carbon is involved in this bridge formation, right? Bridge formation. So this is not possible. The other alpha position is this one. So here the alpha hydrogen is not attached to the bridge head carbon, okay, because this carbon is not involved in bridge formation. So yes, this alpha hydrogen will show tautomerism. Okay, so here tautomerism is possible. Okay, it will be exhibited in this case. That means 3 only will be the correct answer. Okay, so option number B, 3 only, because 1 and 2 will not exhibit tautomerism. Question number 5 is from the chapter Aldehydes, Ketones and Carboxylic Acids, and the question is the correct order of strengths of carboxylic acids. Okay, so we have to find the correct order of their strength. Now let's see, we can see that in the first one there is no extra group in the ring, whereas in second and third there is an extra group, that is oxygen, present within the ring. Okay, so we know that oxygen is an electronegative atom, electronegative. Therefore, it will show electron withdrawing effect. Okay, electron withdrawing effect, and it means it will show minus I effect. Also, we know that minus I effect will increase the strength. Okay, it will increase acidic strength. So it means that the second and the third one will be stronger acids as compared to the first one. Okay, so first one will have minimum strength. Then out of second and third, which one will be strongest? We know that it also depends on the distance of that electronegative atom. So in the second one, this oxygen seems to be closer to this carboxylic group, whereas in the third one this is at a distant. Okay, so this is 1 2 3 4 at fourth position. Here it is 1 second third. Okay, so this is closer in second, therefore second will be the strongest acid, whereas third will be less than the second one but more than the first one. Okay, so this will be the correct sequence. Now let's see this sequence. You can see in option number C. Okay, second, then third, and then one. Okay, so option C is the correct answer. Question number 6 is from the chapter Hydrocarbons, and the question is the compound that will react most readily with gaseous bromine has the formula. Okay, so first of all gaseous bromine is mentioned, and we know that bromine naturally exists in the liquid state. That means for this reaction to take place, bromine has to first get converted into the gaseous state, and for that a very high temperature will be required, right? Very high temperature required. Otherwise the bromine will come back to its natural state, that is liquid state. Okay, and at this high temperature what type of reaction will take place? Free radical substitution reaction will take place. Free radical substitution reaction, and the rate or the reactivity of this reaction will depend on the stability of the free radical. Okay, free radical. Now we know that the most stable free radical or the most reactive free radical is that of benzene. Okay, but here benzene is not mentioned. So after that, the most reactive one will be the allylic free radical. Okay, allylic free radicals are very reactive. Allylic means what? Suppose we have carbon-carbon double bond, then a carbon that comes next to a doubly bonded carbon will be known as the allylic carbon. Okay, so for this, that means allylic free radical, more than two carbons are required. Okay, more than two carbon compound, and the compound must be an alkene, right? Because the double bond is required. Now in the given options we have, the first one is an alkene, second one is also an alkene, third one is an alkyne. So this will not be the most reactive one. Okay, and the fourth one is an alkane. This is also not the most reactive one, because for that we need an alkene. Okay, and out of first and second alkene, the first one contain only two carbons. Okay, carbon carbon double bond, so this will not make allylic free radical, but the second one, that is propene, will make propenyl free radical, and that will be an allylic free radical. Okay, so let's see the structure here. We have alkene, the propene, CH3 CH double bond CH3. Okay, now it will react with bromine, Br2. So first of all, a free radical will be formed as an intermediate. Intermediate will be the free radical CH2 CH double bond CH2. So this is the free radical. And which type of free radical? Allylic free radical. Now this will be very stable due to resonance. Okay, so this is stable, very stable due to resonance, and due to that its reactivity will be very high. Okay, reactivity very high, so it will be highest among all the other options. Okay, so option B will be the correct answer. It will react most readily with gaseous bromine. Okay, option B is the correct answer. Question number 7 is from the chapter Chemical Bonding and Molecular Structure, and the question is, which one of the following compounds shows the presence of intramolecular hydrogen bond? Okay, so intramolecular means the hydrogen bond is present within the molecule. Okay, within the molecule, not in between the molecule, that is in the case of intermolecular bond. Okay, so options are concentrated acetic acid, H2O2, HCN, and cellulose. We know that cellulose is a very complex molecule, right? It is a very complex molecule, therefore it contains hydrogen bond within the molecule also. Okay, whereas these three are simple molecules, so there are only intermolecular hydrogen bonds. Intermolecular hydrogen bonds are present in these molecules, whereas in cellulose intramolecular hydrogen bond is also present. So option D will be the correct answer. Question number 8 is from the chapter Electrochemistry, and the question is, the molar conductivity of a 0.5 mole per decimeter cube solution of silver nitrate with electrolytic conductivity of 5.76 into 10 to the power minus 3 S per centimeter at 298 Kelvin is. Okay, so we have to find out the molar conductivity. What are the values given in the question? 0.5 mole per decimeter cube. We know that 1 decimeter cube means 1 liter. Okay, so this is 0.5 mole per liter. This is the molarity. Okay, number of moles per liter of the solution is molarity. So molarity is given. Then electrolytic conductivity, that means the value of K kappa is given. Okay, now we know that the molar conductivity is equal to K into 1000 divided by molarity. Okay, so we simply have to put the values here. K is equal to 5.76 into 10 to the power minus 3 into 1000, that means 10 to the power 3. So this will cancel out, and here we have molarity, that is given as 0.5. Okay, so this is 557.6 divided by 5. Okay, and On dividing it, you will get 11.52. So the correct answer will be option number C, 11.52 Simon centimeter square per mole. Okay, so option C will be the correct answer. Question number 9 is from the chapter Chemical Kinetics, and the question is, the decomposition of phosphine on tungsten at low pressure is a first order reaction. It is because the option A, rate of decomposition is very low, option B, rate is proportional to surface coverage, option C, rate is inversely proportional to surface coverage, and option D, rate is independent of the surface coverage. So the correct answer will be that rate is proportional to surface coverage. Okay, so option B will be the correct answer, right? What happens at low pressure? At low pressure, the surface area covered is proportional to the partial pressure of the phosphine. Okay, partial pressure of phosphine. Therefore, this rate depends on the surface coverage. So option B will be the correct answer. Question number 10 is from the chapter Surface Chemistry, and the question is, the coagulation values in millimoles per liter of the electrolytes used for the coagulation of As2S3 are given below. So first one is NaCl, its value is given as 52. Second one is BaCl2, its value is 0.69, and the third one is MgSO4, magnesium sulfate, its value is 0.22. The correct order of their coagulating power is, okay, so the coagulation values are given and we have to find the coagulation power. So what is the relation between coagulation values and coagulation power? We know that the coagulation power is inversely proportional to the coagulation value. Okay, that means lower the coagulation values, more will be the coagulation power. So which has the lowest value? The third one. Okay, this has lowest value. That means magnesium sulfate will have the highest coagulation power. Okay, because these are inversely proportional. So magnesium sulfate will have highest coagulation power. Then the second one is 0.69. So the next one will be BaCl2. And 52 is maximum value, so its power will be minimum. Okay, so NaCl will have minimum power. Magnesium sulfate means number 3, then number 2, and then NaCl, that is number 1. So this will be the sequence. So the correct option will be option number D. Okay. Question number 11 is from the chapter Electrochemistry, and the question is, during the electrolysis of molten sodium chloride, the time required to produce 0.10 mole of chlorine gas using a current of 3 amperes is. Okay, so we have molten NaCl. This will get dissociated into Na plus ion and Cl minus ion. This Na plus ion will undergo reduction at the cathode, whereas this chloride ion will undergo oxidation at the anode. And after the oxidation, what do we get? We'll get chlorine gas, that is Cl2. So the amount of chlorine gas liberated is given as 0.10 mole. Okay, so number of moles is given 0.10, and the amount of current passed, that is I, is equal to 3 amperes. We have to find out the time required for this reaction, right? So for that, we'll use Faraday's first law of electrolysis, using which we can write that weight of the element deposited will be equal to Z into current I into time t. Okay, and we know that Z is equal to equivalent weight upon the Faraday's constant, that is 96500. Okay, and equivalent weight is equal to molecular weight upon valency factor. Okay, divided by 96500. So this will be the value of Z. So let's put this value. This side we have weight and this side we have Z is equal to molecular weight upon valency factor. Here we have 96500 into current and time. Now this molecular weight will come this side. So weight by molecular weight will become number of moles. Okay. So number of moles N will be equal to current into time upon valency factor into 96500. Now let's put the values. Number of moles is given as 0.10. Current is given as 3 amperes. Time is not known. Then valency factor is 2 because there is transfer of 2 electrons during the conversion of chloride to chlorine gas, right? Into 96500. So we have to find out the value of T, that will be equal to 0.1 into 2 into 96500 upon 3. But this time will come in seconds, and in the options the time is mentioned in minutes, so we'll divide it by 60 to get the time in minutes, and on solving this we'll get 107 minutes. Okay. Now if you look at the options, there is not any option which has 107 minutes, but the closest option will be 110 minutes. So option C will be the correct answer. Now question number 12 is from the chapter Structure of Atom, and the question is how many electrons can fit in the orbital for which n equals to 3 and L equals to 1. So L equals to 1, that means we are talking about the p subshell, right? You know, for L equals to 0 we are talking about S subshell. If L equals to 1 it means p subshell. If it is equal to 2 then D. And similarly if L equals to 3 that means F subshell. Okay, so since L is equal to 1 we are talking about p subshell. Now how many orbitals are there in p subshell? 3 orbitals. Okay, so it will be 3 orbitals here, and when we fill the electrons then it will be 1 2 3 4 5 6 for 3p. Okay, and we can say that there are 6 electrons in the p subshell, but p subshell consists of 3 orbitals, right? This is orbital 1, this is orbital 2, this is orbital 3. Okay, so 6 electrons are present in 3 orbitals, in all the 3 orbitals of p subshell, but in the question orbitals is not mentioned. Okay, orbitals is not mentioned. It is mentioned as orbital, that means a single orbital. So we can see that in each orbital there are 2 electrons only. Okay, in total of 3 orbitals there are 6 electrons, but in each orbital there are 2 electrons. So according to that 2 should be the correct answer. Okay, so there has been a lot of confusion in this question because many people think that 6 will be the correct answer, but since the question mentions orbital, a single orbital, not orbitals, so it will be 2 only. Okay, option B will be the correct answer. Question number 13 is from the chapter Thermodynamics, and the question is for a sample of a perfect gas, when its pressure is changed isothermally from Pi to Pf, the entropy change is given by. Okay, so entropy change delta S is equal to dq by T, right? Where Q is the change in heat and T is temperature. Now we have to take integration because the value should be between initial pressure and final pressure. Now we know that temperature is constant, so it can be taken outside. Here we have dq, initial pressure and final pressure. Now we know that change in heat is equal to change in work done. Okay, so dq will be equal to dw and change in work done will be equal to pdv. If you know the basic concept of thermodynamics, you can understand why dw is equal to pdv. Okay, now let's put this value here. It will be equal to 1 by t integration of P dV, and the limit is initial and final pressure. Now the question mentions that the sample is of perfect gas, that means ideal gas. So we know that for an ideal gas PV equals to nRT. So from here P is equal to nRT by V. Okay, so can we put this value of P in this equation? Yes. So delta S will be equal to 1 by T integration of nRT upon V. Okay, in place of P we wrote nRT by V into dV. Limits are initial and final pressure. Again nRT is constant, so it can be taken outside. So it will be nRT upon T integration of dV by V. Okay, initial and final pressure. T will be cancelled, so it will be nR integration of dV by V. And what will be the integration of dV by V? It will be ln V. Okay, so nR ln V, and the limits are initial and final pressure, so it will become nR ln V final upon V initial, right? So till here you understood, but the options are given in terms of pressure, not volume. So for that we have to consider Boyle's law. Boyle's law. What does Boyle's law say? It says that at constant temperature, because the question mentions that the process is isothermal, so the temperature is constant, and Boyle's law say that at constant temperature PV is constant. Okay, that means P initial into V initial will be equal to P final into V final. Okay, so from here we can find the value of V final upon V initial, that will be equal to P initial upon P final. So we can put this value here. So it will become delta S equals to NR ln P initial upon P final. Got it? So this will be the correct relation. And let's match it from the options. So in option number C, we have this value delta S equals to NR ln P initial upon P final. That means option C will be the correct answer. Question number 14 is from the chapter solutions, and the question is the Van 't Hoff factor I for a dilute aqueous solution of the strong electrolyte barium hydroxide. Okay, so strong electrolyte means what? It will dissociate completely. Dissociate completely. Now we have barium hydroxide, that is BaOH whole twice. So it will get dissociated into Ba2 plus ion and 2OH minus ions, right? Now we have to find out the Van 't Hoff factor I. So that is equal to abnormal colligative property. Abnormal colligative property upon normal colligative property, right? Normal colligative property. Now what does abnormal colligative property indicate? It indicates the number of ions produced. Okay, that means number of particles after dissociation. After dissociation. Whereas normal colligative property indicates number of particles before dissociation. Okay, number of particles before dissociation. So how many particles are produced after dissociation? That means how many ions are produced? 3 ions total. Okay, 1 barium ion and 2 OH minus ions. So 3 upon the number of particles before dissociation, only 1. Okay, only 1 mole of barium hydroxide was there. So 1. So it is equal to 3. Okay, that means Van 't Hoff factor will be equal to 3. So option A will be the correct answer. Now one thing that you can remember here, that the Van 't Hoff factor for the case of dissociation will always be more than 1. Okay, for dissociation, Van 't Hoff factor will be more than 1, and for the case of association, when two molecules join to form another molecule, in that case Van 't Hoff factor will be less than 1. Okay, so this is the case of dissociation, therefore it is more than 1, that is 3. So option A is correct answer. Question number 15 is from the chapter equilibrium, and the question is the percentage of pyridine that forms pyridinium ion in a 0.10 molar aqueous pyridine solution is. Okay, Kb for pyridine is given. Now we know that pyridine is a weak base, right? So on reaction with water, let's write down the reaction. C5H5N is pyridine. Now it will react with water to give pyridinium ion, that is C5H5NH, and there will be a positive charge in nitrogen, plus OH minus ion. Okay, now what will be the degree of dissociation? Alpha will be equal to Kb upon C. Okay, Kb is the equilibrium constant for weak base, right? And its value is given in the question. So let's put the value. It is given as 1.7 into 10 to the power minus 9 upon C. C is the molarity or the concentration, okay, molar concentration. So that is given as 0.10 molar, so 0.10. Now on solving this, we'll get 1.3 into 10 to the power minus 4. This is the degree of dissociation, but we have to find out the percentage of pyridine formed, okay. So percentage will be equal to 1.3 into 10 to the power minus 4 into 100, okay. We'll multiply it by 100 to get the percentage. It will be equal to 1.3 into 10 to the power minus 2, or we can write 0.013 percentage, okay. So 0.013, that means option C will be the correct answer. Question number 16 is from the chapter solid state, and the question is, in calcium fluoride having the fluoride structure, the coordination number for calcium ion Ca2 plus and fluoride ion F minus R. Okay, so what do you mean by coordination number? It means the number of nearest surrounding atoms. Okay, number of nearest atoms surrounding the central atom, right? Surrounding the central atom. Now, we have calcium fluoride, that means CaF2. In this, we have two types of ion, Ca2 plus ion and F minus ion, right? This Ca2 plus ion is present at the corner and face center in the structure, okay? In the fluoride structure, it is present at corner and face center. Whereas fluoride ion is present in the tetrahedral voids. Tetrahedral voids. So each calcium ion is surrounded by 8 fluoride ion. Surrounded by 8 fluoride ion. Whereas each fluoride ion is surrounded by 4 calcium ion. Okay. So the coordination number of calcium ion will be 8, whereas the coordination number of fluoride ion will be 4. Okay. So 8 and 4, that means option D will be the correct answer. Question number 17 is from the chapter electrochemistry, and the question is, if the E0 cell for a given reaction has a negative value, which of the following gives the correct relationships for the values of delta G0 and K equilibrium? Okay, so we know that delta G0 is equal to minus NF E0. Okay, it is given that this E0 is negative, and we already have a negative sign here. That means negative and negative will become positive. Okay, so it shows that delta G0 will be positive. Delta G0 will be more than 0. Okay. Now the second thing is K equilibrium. So for that we'll consider the equation delta G0 equals to minus 2.303 RT log K. Okay. Now we know that this delta G0 is positive, and on the right hand side we have a negative sign here. That means the right hand side can be made positive when this log K will be negative. Okay, so negative and negative will become positive. Okay, so for delta G0 to be positive, log K must be negative. Okay, it should be less than 0, and in which case log K is less than 0? When K is less than 1. Okay, so when K is less than 1, log K is less than 0. So we can say that K is less than 1. That means which option should be the correct one? Delta G0 more than 0 and K equilibrium less than 1. So option B will be the correct answer. Question number 18 is from the chapter solutions, and the question is, which one of the following is incorrect for ideal solution? Okay, so we know that in an ideal solution delta H of mixing, that means enthalpy of mixing, is 0. So option B cannot be the answer here, because this is correct for ideal solution and we have to find out the incorrect. Okay, also delta V, that means volume of mixing, is 0, right? And we know that delta U is equal to delta H minus P delta V. Okay, and here delta H is 0, delta V is also 0, that means delta U will also be 0. Okay, so third one is also correct. Fourth one is also correct, that delta P is equal to P observed minus P calculated by Raoult's law equals to 0. Okay, because we know that an ideal solution obeys Raoult's law. Okay, and in that the change in pressure, that is pressure observed minus the pressure calculated by Raoult's law, is equal to 0. Okay, so this is also correct. Now let's talk about the first one. It will be incorrect obviously because this is only left. But why? Because delta G is equal to delta H minus T delta S, right? And we know that for ideal solution, delta S, that means entropy of mixing, is not 0. Okay, so here this delta S is not 0, delta H is 0. So this delta G will also be not equal to 0. Okay, because this delta is not 0. So first option will be the incorrect one. That means option A will be the correct answer. Question number 19 is from the chapter Equilibrium, and the question is the solubility of solid AgCl with solubility product 1.6 into 10 to the power minus 10 in 0.1 molar NaCl solution would be. Okay, so we have AgCl, and in aqueous state it will dissociate into Ag plus ion and Cl minus ion. If the solubility of AgCl is S, that means the solubility of Ag plus ion will also be S, and that of chloride ion will also be S. Okay. Now we have NaCl also here. It will also dissociate into Na plus and Cl minus. That means Cl minus ion is common. Okay. So here it is given that there are 0.1 molar NaCl. That means Cl minus from this will also be 0.1 molar. Okay. So the total concentration of chloride ion will become S plus 0.1. Okay, S here and 0.1 here. Okay, so this is the total concentration of chloride ion. Now we have to find KSP. KSP is equal to the concentration of Ag plus ion into the concentration of chloride ion. Okay, now that of Ag plus is S, whereas the concentration of chloride ion is S plus 0.1. So it will become S square plus 0.1 S, right? Now KSP is mentioned in the question. It is equal to 1.6 into 10 to the power minus 10. On the right hand side, S square can be ignored because, let's ignore it, because S is very less as compared to 0.1. Okay, so it can be ignored. That means this KSP will be equal to 0.1 S. Okay, so from here we can find out the value of S. That will be equal to 1.6 into 10 to the power minus 10 upon 0.1. So that will be equal to 1.6 into 10 to the power minus 9. Okay. So option C will be the correct answer. Okay. Question number 20 is from some basic concepts of chemistry, and the question is, suppose the elements X and Y combine to form two compounds XY2 and X3Y2 when 0.1 mole of XY2 weighs 10 grams and 0.05 moles of X3Y2 weighs 9 gram, then the atomic weights of X and Y. Okay, so we have two compounds. First one is XY2 and the second one is X3Y2. Okay, now the number of moles of XY2 is given as 0.1. Okay, it is given in the question that 0.1 mole of XY2 weighs 10 gram. That means the given weight for XY2 is 10 grams and the number of moles is 0.1. Similarly for X3Y2, the number of moles given is 0.05 and the given weight is 9 grams. Okay, now what will be the molecular weight? Molecular weight of XY2. Suppose the atomic weights are X and Y respectively, then the molecular weights will be X plus 2Y. Okay. Similarly, the molecular weight for X3Y2 will be 3X because there are 3X plus 2Y are there, so 2Y. Okay, this will be the molecular weight of this compound. Now, we know that the number of moles is equal to given weight upon molecular weight. Okay, so number of moles is 0.1 is equal to given weight, that is 10, divided by molecular weight, that is X plus 2Y. Now using this we can say that X plus 2Y will be equal to 10 divided by 0.1, that is 100. Okay, so let's say this is equation number 1. Similarly, for X3Y2, number of mole, that is 0.05, will be equal to given weight, that is 9 grams, upon molecular weight, that is 3x plus 2y. So from here we can say that 3x plus 2y will be equal to 9 divided by 0.05, that is 180. Okay, so let's say this is equation number 2. Now using these two equations we can find out the value of x and y. Okay, so for example, if we subtract equation 1 from equation 2, subtracting equation 1 from equation 2, so 3x plus 2y minus x plus 2y. So 2y will be cancelled. So 3x minus x will be 2x. And on the right hand side, 180 minus 100, that is 80. Okay. So x will be equal to 80 divided by 2, that is 40. Okay. So this is the atomic weight of x. Similarly, if we put the value of x in any one of the equations, we'll get the value of y. Okay. For example, if we take this one, then x is equal to 40. So 3x, that means 120. 3 into 40 is 120 plus 2y equals to 180. 2y will be equal to 180 minus 120, that is 60, and y will be equal to 60 divided by 2, that is 30. Okay, so this will be the atomic weight of y, 30. So the answers will be 40 and 30. Okay, so option B, 40 and 30 will be the correct answer. Question number 21 is from the chapter Electrochemistry, and the question is the number of electrons delivered at the cathode during electrolysis by a current of 1 ampere in 60 seconds is, okay, charge on the electron is given as 1.6 into 10 to the power minus 19 coulomb. Now we know that the charge Q is equal to number of electrons into the electronic charge. Okay, N is number of electrons, whereas E is charge on each electron. Okay, charge on the electron, right? Also we know that Q is equal to current into time. Okay, so let's put this, charge Q is equal to current into time, and that is equal to N into E. Now current here is given as 1 ampere, time is given as 60 seconds, number of electrons is unknown, that we have to find out, and the charge on electron is 1.6 into 10 to the power minus 19 coulomb. So from here we can find out the number of electrons N, that will be equal to 1 into 60 upon 1.6 into 10 to the power minus 19. Okay, and on solving this you'll get 3.75 into 10 to the power 20. This will be the number of electrons required. That means option B will be the correct answer. Now question number 22 is from the P block elements, and the question is boric acid is an acid because its molecule. So let's see the structure of boric acid. We have a boron, then 3 OH groups are there, and one vacant orbital is there. Okay, now when this reacts with water molecule, then it accepts OH minus of water molecule and leaves H plus ion. Okay, and that H plus ion further reacts with other water molecules to give H3O plus ion. Okay, so the final products will be B, 4 OH groups will be attached to this, right? Because 3 OH groups were already there and one OH has been accepted from water molecule. So 4 OH groups, and then H plus ion will be left, or this H plus will react with other water molecules to form H3O plus ion. Okay, so these are the products. Now what do we see? That the boric acid has accepted OH minus ion. Okay, and that is the reason it is known as an acid. And in fact it is an example of monobasic Lewis acid. Okay, Lewis acid are those which accept a lone pair of electrons. Okay, so from water it also accepts lone pair of electrons because water has 2 lone pairs of electrons. Okay, now the first option is that combines with proton from water molecule. No, it does not combine with proton. It takes OH minus ion. Okay, and it leaves the proton. Now the second option says contains replaceable H plus ion. No, the H plus ion is not replaceable here, so this is also incorrect. Third one is gives up a proton. So yes, it gives up a proton, but it does so only after receiving OH minus ion. Okay, and the reason why it is known as acid or Lewis acid, because it accepts the lone pair of electron or it accepts the OH minus ion. Okay, so third one is correct statement, but it is not the reason why it is an acid. So the correct one will be the last one, that it accepts OH minus from water, releasing a proton. So this will be the proper statement. Okay, so option D will be the correct answer. Question number 23 is again from the P block elements, and the question is, aluminium trifluoride is soluble in hydrogen fluoride only in the presence of potassium fluoride. It is due to the formation of, okay. So when potassium fluoride is not present, then aluminium trifluoride will not dissolve in hydrogen fluoride. The reason is that anhydrous hydrogen fluoride, anhydrous hydrogen fluoride is a covalent molecule. Okay, it is a covalent molecule and it contains strong hydrogen bonds. Okay, strong hydrogen bonds. So these are bonded strongly by the hydrogen bonds like this. Hydrogen fluorine. Okay, this is hydrogen fluoride. Now there is a bond formation, hydrogen fluorine, like this. Okay, now due to this, free fluoride ions are not available for complex formation. Okay, fluoride ions not available for complex formation, but aluminium trifluoride has to make complex. So for that, potassium fluoride is required. The reason is that when potassium fluoride is added, then what happens, aluminium trifluoride will be able to make a complex. And let's see what will be the complex formed. We have aluminium trifluoride, it will react with potassium fluoride and it will form a complex K3Al F6. What is this? This is potassium hexafluoro hexafluoroaluminate. Okay, because the maximum coordination number of Al3 plus is, the coordination number of Al3 plus is 6. Okay, therefore it makes AlF6 3 minus ion. Okay, and then when it reacts with potassium, it forms this complex, that is potassium hexafluoroaluminate, and this is a soluble complex. And due to the formation of this complex, aluminium trifluoride will get solubilized in hydrogen fluoride. Okay, so it gets solubilized in hydrogen fluoride due to this complex, due to the formation of this complex. Okay, so which complex is formed? Potassium hexafluoroaluminate. So this is given in option number C. Okay, K3Al F6. Option C will be the correct answer. Question number 24 is from the chapter electrochemistry, and the question is, zinc can be coated on iron to produce galvanized iron, but the reverse is not possible. It is because option A, zinc has higher negative electrode potential than iron. Option B, zinc is lighter than iron. Option C, zinc has lower melting point than iron. And option D, zinc has lower negative electrode potential than iron. Okay, so this is a very common question. Here we just have to compare the reactivity of zinc and the other metal, that is iron in this case. Okay, so we know that the reactivity depends on the standard reduction potential. So let's write down the standard reduction potential of zinc first. Zn2 plus 2, Zn, it is minus 0.76 volt, whereas the standard reduction potential of Fe2 plus 2Fe is minus 0.44 volt. Now we know that more negative the standard reduction potential, more is the reactivity of the metal. Okay, so which one is more negative? Zinc. Okay, minus 0.76 volt. So we can say that SRP, that is standard reduction potential of zinc, is more negative as compared to that of iron. That means zinc is more reactive. more reactive metal as compared to iron. Now, if it is reactive, why does it protect the iron? The reason is that the zinc undergoes oxidation first, okay, because this is more reactive, right? So it will oxidize first and it will experience the corrosion. So we can say that the zinc will sacrifice itself to protect the iron, okay. But when the reverse is done, that means when zinc will be coated with iron, iron will not get reacted first, okay, so it will not be able to protect the zinc, right? So one will be the correct answer? Option A, zinc has higher negative electrode potential than iron, and that is the reason it is more reactive than iron. So it will react first, thus protecting the iron from corrosion. Question number 25 is from the chapter S block elements, and the question is, the suspension of slaked lime in water is known as. Options are aqueous solution of slaked lime, lime water, quick lime, or milk of lime. Okay, so we know that slaked lime is nothing but calcium hydroxide, okay, and it is formed when calcium oxide reacts with water. Okay, so first calcium oxide, that is quick lime. Quick lime is calcium oxide, right? And when it reacts with water, then what happens? Calcium hydroxide, CaOH2, is formed, and this is known as slaked lime. Now this slaked lime is sparingly soluble in water. Sparingly soluble. And this is the reason a suspension of this slaked lime is formed, okay, and its suspension is known as milk of lime, okay. So a suspension is formed that is known as milk of lime. So which one will be the correct answer? Option D will be the correct answer. Question number 26 is from the chapter Chemical Bonding and Molecular Structure, and the question is, the hybridizations of atomic orbitals of nitrogen in NO2 plus, NO3 minus and NH4 plus respectively are. Okay, so let's find the number of hybrid orbitals. Number of hybrid orbitals. What is the formula to calculate number of hybrid orbitals? It is half number of valence electrons in the valence shell of central atom, in the valence shell of central atom, plus number of monovalent atoms surrounding the central atom, minus the charge. Okay, so let's find out one by one. The first species mentioned is NO2 plus. Okay, so what is the structure of NO2 plus? It looks like this. We have N double bond O, this side also double bond O, and there is a plus charge. Okay, so this is the structure of NO2 plus. Now we have to find the number of hybrid orbitals. So half the number of valence electrons in the valence shell of the central atom, that is nitrogen, is 5, right? So 5 plus number of monovalent atoms is 0, because it is only bonded to oxygen, which is divalent atom, okay, not monovalent. So there is 0 monovalent atoms, minus charge. So there is a plus 1 charge, so 1. Now on calculating this, what do we get? We get 2. Okay, and we know that when the number of hybrid orbitals is 2, it means the hybridization is sp hybridization. Okay, now the second one is NO3 minus. NO3 minus. What is the structure of NO3 minus? So it is N, this side we have oxygen, this side double bond O, and this side O minus. Okay, this is the structure of NO3 minus. Now let's calculate the hybrid orbitals. So half, again the number of valence electrons in nitrogen is 5, plus monovalent atom 0, because it is also bonded to oxygen only, minus what is the charge? Minus 1. Okay, so now minus and minus 1 will become plus 1. So 5 plus 1 divided by 2 will be 3. So what is the hybridization? When the number of hybrid orbitals is 3, it will be sp2 hybridization. Okay, and the last one is NH4 plus, right? NH4 plus. So let's see the structure first. We have nitrogen here with plus charge, 3 hydrogens this side like this, and 1 hydrogen here. Now let's find the number of hybrid orbitals. So half. Again, the number of valence electrons in nitrogen will be 5, plus how many monovalent atoms are there? 4, because hydrogen is a monovalent atom. So 4 minus the charge is plus 1. So 1. Now on calculating this, we get 4. Okay, and when the number of hybrid orbitals is 4, it means the hybridization is sp3. So the hybridizations of these species will be sp, sp2 and sp3 respectively. Okay, so let's see sp, sp2 and sp3. That means option D will be the correct answer. Question number 27 is from the chapter Equilibrium, and the question is, which of the following fluorocompounds is most likely to behave as a Lewis base? So in one of the previous questions we had discussed about Lewis acid. Do you remember that? We had discussed that Lewis acid is the one which can accept a lone pair of electron. Okay, so it is lone pair acceptor. On the other hand, if we talk about the Lewis base, it is the one which can donate the lone pair. Okay, so it is lone pair donator. Now here we have to find out which one will behave as Lewis base. That means we have to check which one will be able to donate a lone pair of electron. Okay, so let's see one by one. In the first one we have SiF4. Now in this we know that the octet is complete. Okay, octet complete, but there is a vacant d orbital. Okay, so there is a vacant d orbital, so it will try to accept the lone pair of electron in this vacant d orbital. Okay, so it will behave as a Lewis acid. Now the second one is BF3. Now we know that boron has incomplete octet in this. Okay, so the octet is incomplete. So it is quite obvious that it will accept the lone pair of electron to complete its octet. Okay, so it will also behave as a Lewis acid. Third one is PF3. Now PF3, here the octet is complete. Octet complete, plus there is a lone pair of electron also. Okay, lone pair of electron. So if we look at the structure, we have phosphorus. Here we have fluorine, 3 fluorines and 1 lone pair of electron on the phosphorus. That means it has extra lone pair, so it will act as the lone pair donator. Okay, so it will donate the lone pair, donate lone pair of electron. That means it will behave as the Lewis base. Okay, now let's check the last one. It is CF4. So here carbon has complete octet. Okay, so octet is complete, but there is no lone pair of electron. But it is quite obvious that the one which is behaving as a Lewis base is the third one, that is PF3, due to the presence of a lone pair of electron on the phosphorus atom. Okay, so option C will be the correct answer. Question number 28 is from the chapter Chemical Bonding and Molecular Structure, and the question is, which of the following pairs of ions is isoelectronic and isostructural? Okay, so isoelectronic means what? Having same number of electrons, same number of electrons or valence electrons, and isostructural means having same structure or same geometry. Now if you look at the options carefully, you can see that only 4 types of ions are present here. Okay, ClO3 minus, SO3 2 minus, CO3 2 minus, and then NO3 minus. Okay, so different combinations are given, but total types of ions present here are only 4. So let's see these 4 types of ions in detail. ClO3 minus. So if we draw the structure here, this is chlorine, double bond O, and O minus, and there is a lone pair of electron on the chlorine atom. Okay, so first let's find the steric number. Steric number will give you the structure or the shape of the compound. Okay, so steric number is equal to total number of atoms which are bonded to the central atom. So here total 3 oxygens are bonded, so 3 plus total number of lone pairs. So one lone pair is on chlorine atom, so 3 plus 1 is 4. Now when the steric number is 4, it means the shape will be tetrahedral. Tetrahedral or pyramidal. Now we'll find the number of electrons as well, because we have to compare the number of electrons. So number of electrons, how many valence electrons in chlorine? Total 7 valence electrons, plus each oxygen has 6 valence electrons, and there are total 3 oxygens, so 3 into 6, plus here you can see one negative charge is also there, so one more electron. So total number of electrons will come out to be 26, right? Similarly, we'll find the steric number and number of electrons for other species as well. So the second one is SO3 2 minus. Here we have sulfur, then double bond O, here O minus, and then again one lone pair on the sulfur. Okay. First we'll find the steric number as usual. So steric number, that is equal to total number of atoms bonded to the central atom, that is 3 oxygen, plus one lone pair is there, so 3 plus 1, again it is equal to 4. That means again the shape will be tetrahedral or pyramidal. Now number of electrons. How many electrons in the valence shell of sulfur? 6 electrons, plus 3 oxygen, so 3 into 6 for oxygen, and 2 negative charges are there here, so plus 2. Okay, so it will come out to be 26. So if you compare 1 and 2, you can see that the shape is also same and the number of electrons is also same. That means isoelectronic and isostructural as well. Okay, let's see other ones also. So the third one is CO3 2 minus. Now here we have carbon, double bond O, this side single bond O minus and O minus. Now steric number, total number of atoms bonded to carbon 3, and how many lone pair of electrons? 0. Okay, here carbon has no lone pair of electron, so total steric number will be 3 this time. That means the shape will be trigonal planar. Now we'll find the number of electrons. So how many valence electrons in carbon? 4. Okay, plus 3 oxygens are there, so 3 into 6, and 2 minus charge are also there, right? So 2 more electrons, and when we add them up, we'll get 24 electrons. Okay, and the last type of species given here is NO3 minus. So similarly, we'll find the structure as well as number of electrons for this. So NO3 minus, that means nitrogen, double bond O, single bond O minus, single bond O minus. Here nitrogen will have a positive charge, okay, plus charge. Steric number will be 3 oxygen, so 3 plus how many lone pair of electrons? 0. Okay, lone pairs are 0, so 3. Again, that means the shape will be trigonal planar. Now number of electrons. How many electrons in the valence shell of nitrogen? 5 electrons, plus 3 oxygen atoms, so 3 into 6, and 2 minus charge are also there, right? But 1 plus charge is also there, so 1 plus will cancel out 1 minus, that means only 1 more electron. So here when we add them up, we'll get 24. So if you compare 3 and 4, also you will get same number of electrons, that means isoelectronic, and same shape also, that is trigonal planar. But we have to choose any one. So according to this, the first option should also be correct, that ClO3 minus and SO3 2 minus are isostructural and isoelectronic, because both have 26 electrons and both have tetrahedral shape or pyramidal shape. Okay, and if we see the second one, that is CO3 2 minus and NO3 minus, also they have same number of electrons, that is 24, and same shape, that is trigonal planar. But we have to choose only one option. So the first one will be more preferable, because in second one we can see that here the carbon does not have any charge, but nitrogen has a plus charge. Okay, so there is a change in the central atom. But in the first and second one, ClO3 minus and SO3 2 minus, chlorine and sulfur both have a lone pair of electron on them. So if we have to choose one, then we can prefer the option number 1, but otherwise both are isostructural and isoelectronic. Okay, and C and D cannot be correct because these are clearly wrong option, because ClO3 minus has 26 electrons, whereas CO32 minus has 24 electrons. Okay, similarly both one can also be, cannot be correct one. Okay, so only options are A and B, but we prefer option A. Okay. Question number 29 is from the S block elements, and the question is, in context with beryllium, which one of the following statements is incorrect? Okay, so let's check. The first statement says its hydride is electron deficient and polymeric. Now this is a correct statement. Beryllium hydride means BeH2. Now we know that beryllium has 2 electrons in its outermost shell and each hydrogen has 1 electron. So this is how bond formation takes place, and total number of electrons around beryllium in beryllium hydride is 4 now. Okay, so we can say that the octet is incomplete. Incomplete octet. And this is the reason why beryllium hydride is considered as electron deficient. Okay, now polymeric because it exists in polymeric form and the structure looks like this. These are beryllium and these are hydrogens. Okay, so this is how the polymeric structure looks. So this is a correct statement. Now the second statement says it is rendered passive by nitric acid. This is also a correct statement because rendered passive means it becomes inert by the reaction with nitric acid. Okay, due to the formation of an oxide layer. Okay, so formation of an oxide layer takes place, and due to this the beryllium becomes inert. Okay, that means the oxide layer protects the beryllium from further attack of the acid. Okay, now the third statement says it forms beryllium carbide. This is also correct. Okay, so let's see the reaction here. 2 beryllium plus carbon gives beryllium carbide. So this is very simple reaction. Now we come to the last statement. It says its salts rarely hydrolyze. Now this is the incorrect statement because these salts can easily be hydrolyzed. The reason is that the beryllium salts are covalent in nature. Okay, so let's write it down here. Beryllium salts are covalent in nature due to very strong, very small size of the beryllium ion. Okay, due to very small size of beryllium ion, that is Be2 plus ion, and high polarizing power. High polarizing power. This is why they get easily hydrolyzed. Okay, easily hydrolyzed. So this is incorrect and we had to find the incorrect statement. So option D will be the correct answer. Question number 30 is from the chapter redox reaction, and the question is, hot concentrated sulfuric acid is a moderately strong oxidizing agent. Which of the following reactions does not show oxidizing behavior? Okay, so let's see. In the first option, the oxidation state of calcium in calcium fluoride is +2. Okay, and on the product side, the oxidation state of calcium in calcium sulfate is again +2. That means oxidation state is same. Now if we see for fluorine, here on the reactant side it is -1, and on the product side also the oxidation state of fluorine is -1. That means oxidation state did not change. It remained same. So it is not an example of redox reaction. Okay, it is not a redox reaction. So this should be the correct answer because here the sulfuric acid is not behaving as an oxidizing agent, because if oxidation would have taken place, then the oxidation state of calcium would have increased. Okay. Now in the second one, we can see that copper is in its pure element form. So the oxidation state will be 0. Okay. Whereas on the product side, the oxidation state of copper has become +2. Okay, so this time you can see that the oxidation state has increased. Oxidation state of copper has increased from 0 to +2. So this will be a redox reaction. You can check for other elements as well. Now in the third one, again sulfur is in its pure form, so it is 0, oxidation state is 0 on the reactant side, whereas on the product side the oxidation state of sulfur is +4. Okay, here that means oxidation state of sulfur has increased from 0 to +4. This is also redox reaction. And in the last one again, carbon 0 this side, and this side it is +4. Okay, so oxidation state of carbon increased from 0 to +4. You can see in all the reactions, that means except the first one, the oxidation state has increased. Okay, whereas in the first one, oxidation state of all the elements remained same. Therefore option A will be the correct answer. Question number 31 is from the chapter Structure of Atom, and the question is which of the following pairs of d orbitals will have electron density along the axis. Okay, so how many d orbitals are there? There are 5 d orbitals, and these are dxy, dyz, dzx, dx square minus y square, and the last one is dz square. Okay, now the question is asked that which of them will have electron density along the axis. So the correct answer will be the last two, that means dx square minus y square and dz square. Okay, for example, dx square minus y square, let's see the shape. This is your y axis, this is x axis, so the shape is like this. It is double dumbbell shape, right? For all the d orbitals, the shape is like double dumbbell. So here it is along the axis. The electron density is along the axis. Similarly, in case of dz square, these are x axis and y axis. So the shape is like this, and one ring like structure in between. So in both the cases, the electron density is along the axis. So dx square minus y square and dz square. That means which one will be the correct answer? In the last option we have this option number D. Okay, and for others, that is dxy, dyz and dzx, the shape looks like this. Okay, so in these cases you can see that the electron density is in between the axis, not along the axis. Okay, therefore the correct answer will be option number D. Question number 32 is from the P block elements, and the question is the correct geometry and hybridization for ZeF4R. Okay, so ZeF4, this is xenon, then we have 4 fluoride and 2 lone pairs will be left. So we'll find out the steric number first. Steric number means number of atoms bonded to the central atom, that is 4, plus number of lone pairs, so 2 lone pairs, so the steric number is 6. Okay, and when the steric number is 6, that means the hybridization is sp3d2. Okay, hybridization is sp3d2. And what is the other way to find the number of hybrid orbitals? We know that number of hybrid orbitals is equal to half into number of valence electrons in the central atom, okay, plus total number of monovalent atoms plus charges, or plus and minus charges, but there are no charges here, so it will be half. Valence electrons in xenon is 8 plus monovalent atoms bonded are 4. Okay, so half into 12, that is 6 again. Okay, so there are two ways in which you can find the steric number. Okay, so 6 means that the hybridization will be sp3d2. Okay, and sp3d2, that means shape. Question number 33 is again from the chapter P block elements, and the question is among the following which one is a wrong statement. Okay, so let's see. The first one is that I3 plus has bent geometry. So I3 plus, that means one iodine. How many electrons in the valence shell of iodine? 6 electrons, out of which 2 are involved in the bond formation with 2 other iodine. How many electrons left? 4 electrons left. That means 2 lone pair of electrons will be on the iodine atom. Okay, and one positive charge is there. This is your I3 plus. So yes, this has a bent geometry. That means option A will be a correct statement. Okay. Now let's come to the second statement. It says pH5 and BiCl5 do not exist. This is also correct. Why does pH5 not exist? Because overlapping of orbitals are not stable. Okay. And for BiCl5, the main reason is that on moving down the group, the size of the atom increases, right? Let's write it down here. On moving down the group, size of the atom increases, and due to this the stability of +5 oxidation state decreases. Okay, stability of +5 oxidation state is reduced, and which one becomes dominant? +3 oxidation state is dominant. Therefore bismuth cannot form pentachloride. Okay, so this does not exist. Okay, so this is correct statement. Now let's move to the third statement. It says p pi d pi bonds are present in SO2. This is also a correct statement. Okay, because sulfur has vacant d orbitals, so it forms p pi as well as p pi d pi. Okay, so this is also correct statement. Now the last statement says SeF4 and CH4 have same shape. So how to determine the shape? SeF4, what is the steric number? Number of atoms bonded, total 4. And how many lone pair of electrons? 1 lone pair of electron. So total steric number will be 5. That means what will be the hybridization? It will be sp3 dehybridization. So the shape will be trigonal bipyramidal shape. Trigonal bipyramidal shape. Now if we talk about the methane, that is CH4, the steric number is total 4 hydrogens or 4 atoms attached to the central atom, and no lone pair is there, so this will be your steric number only. And when the steric number is 4, it means the hybridization is sp3, and the shape is tetrahedral shape. So you can see that these two do not have the same shape, so this will be the wrong statement, and we have to find the wrong statement, so option D is the correct answer. Question number 34 is from the chapter Coordination Compound, and the question is the correct increasing order of the trans effect of the following species is. So what is trans effect? It is the ability of an attached group. Let's write it down here. The ability of an attached group, or you can say the ability of a ligand to direct substitution at what position? Into a position that is trans to itself. Okay, into position trans to itself. This is known as trans effect. Now if we write the trans effect of various groups in increasing order, it will be water. That means it has very less trans effect, then OH, then NH3, then RNH3, then pyridine, PY, then chlorine, bromine, SCN, that means thiocyanate, then that is nearly equal to that of iodine, that is also nearly equal to NO2. Let's continue from here. That is nearly equal to SO3H, that is nearly equal to C6H5. So all these have almost same trans effect. Okay, then more than this is that of NO. This is nearly equal to CO, that is nearly equal to C2H4, that is nearly equal to Cn minus. Okay, but there is only slight difference. Okay, so let's see. the maximum should be for Cn minus, right? Here in the options, first option and third option, we have Cn minus maximum. Okay, so the correct answer should be out of A and C only. Okay, ammonia cannot be more than Cn minus because it is at this position. Okay, this is very less. Okay, very less. So option B is clearly not correct. In the last option, maximum is bromide. So bromide is here. Okay, this is also less than Cn minus, less than Cn minus. So this is also incorrect. Now out of option A and C, we have to compare the trans effect of bromide and C6H5 minus. Okay, so bromide is at this position here, and C6H5, where is it? It is here. Okay, so which one comes first? C6H5 comes later. Okay, it is more, it is in the second row, right? Bromide comes first. That means bromide is less than cyanide, and also it is less than C6H5. Okay, so C6H5, trans effect of C6H5 should be more than that of bromide. That means which option should be the correct one? Option number C should be the correct one. Okay, Cn minus maximum, then C6H5, then bromide, and then ammonia is very less. So option C will be the correct answer. Question number 35 is from the DNF block elements, and the question is, which one of the following statements related to lanthanons is incorrect? Okay, so let's check. The first statement says that cerium plus 4 solutions are widely used as oxidizing agent in volumetric analysis. See, this is the correct statement. What is the electronic configuration of cerium? It is xenon, electronic configuration of xenon, then 4f1, 5d1 and 6s2. Okay, but in plus 4 oxidation state, it will be that of xenon only. Okay, because these 4 electrons will be removed in the plus 4 oxidation state. So this is a stable compound, and it is used in volumetric analysis as an oxidizing agent. So this is correct statement. Now let's come to the second statement. It says europium shows plus 2 oxidation state. So what is the oxidation state of europium? It is that of xenon, then 4f7, 6s2. Now in plus 2 oxidation state, these 2 electrons will be removed. So what will be left? Xenon and then 4f7. So we know that 4f7 means it is half filled f orbital. Okay, half filled orbital. So this is very stable. Okay, therefore it exists in plus 2 oxidation state. So this is also correct statement. Now the third statement says that the basicity decreases as the ionic radius decreases from Pr to Lu. So we know that from cerium to Lu, the basicity decreases. Okay, basicity decreases. Okay, due to decrease in ionic radii. Ionic radii. Now Pr comes somewhere in between these two. Okay, so obviously from Pr to Lu also the basicity will decrease. So this is also correct statement. Now the last statement is all the lanthanoids or lanthanons are much more reactive than aluminium. So this is incorrect because only few lanthanons are more reactive than aluminium, not all, only about 2 to 3, okay, are more reactive. So option D will be the incorrect one that the question is asked about. So option D will be the correct answer. Question number 36 is from the chapter coordination compound, and the question is Jahn-Teller effect is not observed in high spin complexes of. Okay, so what is Jahn-Teller effect? It is a type of geometric distortion, okay, that occurs in the unsymmetric octahedral complexes. So let's write it down here. It is a geometric distortion. And when does it occur? It occurs in the occurs in unsymmetrical octahedral complexes. Unsymmetrical octahedral complexes. That means when the electrons are filled in unsymmetric manner in the orbitals. Okay, so let's check. The first option is D9. So we'll see for D9 in octahedral complex we have 3 T2G orbitals and 2 EG orbitals, right? Now there are 9 electrons, so we'll start filling these orbitals with 9 electrons. So the filling will start from the bottom, that is T2G orbital. 1, 2, 3, then we'll go to the EG orbital, 4, 5. Now we'll start pairing 6, 7, 8, 9. So this is how all the 9 electrons will be filled in these orbitals. Now if you see in the T2G orbitals, all the electrons are filled in symmetric manner. That means all the orbitals contain 2 electrons. Okay, that means one pair of electron. So there is symmetrical filling here. Symmetrical. Whereas in EG orbital there is unsymmetrical filling. Unsymmetrical, because in one of the orbitals there is one pair of electron, whereas in another one there is a single electron. Okay, so this is unsymmetric filling. That means due to this unsymmetric filling there will be distortion. The geometric distortion will be observed. Okay, that is Jahn-Teller effect will be observed. Jahn-Teller effect will be observed. Similarly, we can check for other options. Second one is D7. So 3 T2G orbital and 2 EG orbitals. Now 7 electrons, 1, 2, 3, 4, 5, 6, 7. Okay. So in T2G there is unsymmetric filling. You can see here. Okay. So again distortion will be observed. Or you can say Jahn-Teller effect will be observed. Now the third one is D8. T2G orbitals and 2 EG orbitals. So 8 electrons, 1, 2, 3, 4, 5, then 6, 7, 8. Now in this case, both the EG as well as T2G have symmetric fillings. Okay, symmetric, because in EG orbitals both the orbitals have single electrons, and in T2G both all the 3 orbitals have a pair of electron each. Okay, so both are symmetric. That means no distortion or no Jahn-Teller effect will be observed. So this should be our answer, but we'll check for the last one as well. We have D4, the last option. So here we have 3 T2G, here we have 2 EG. So 4 electrons, 1, 2, 3 and 4. So you can see in the EG orbital there is unsymmetric filling. Okay, one orbital is empty whereas the other orbital has single electron. So this is unsymmetric, that means distortion will be observed. So which one, in which of them the distortion will not be observed? The third one, D8 orbital, right? So option C will be the correct answer. Now question number 37 is from the chapter Haloalkanes and Haloarenes, and the question is, which of the following can be used as the halide component for Friedel-Crafts reaction? Okay, so what is Friedel-Crafts reaction? It is a reaction in which the alkyl or acyl groups are introduced at the aromatic ring. Okay, so this is introduction of alkyl and acyl groups at the ortho and para positions, of the aromatic ring by the reaction with alkyl or acyl halides. Okay, alkyl and acyl halides in the presence of a catalyst. In the presence of catalyst, and the most commonly used catalyst is anhydrous aluminium chloride. Okay, anhydrous aluminium chloride, that is AlCl3. and we know that anhydrous aluminium chloride is a Lewis acid. So we have this Rx, that is alkyl halide. Now it will react with anhydrous aluminium chloride, AlCl3. We know that aluminium has vacant orbital, so this halide ion will attack the aluminium, and as a result will get a carbocation R plus and AlCl3 X minus ion. Okay. Now this X minus can be any halide ion, for example chloride, bromide, iodide. Okay. Now here this stability of this carbocation will determine the rate of the reaction. Okay, that means more stable the carbocation, more stable the carbocation, more is the rate of the reaction. Okay, is the rate of the reaction, because more stable carbocation is more reactive towards the Friedel-Crafts reaction. Okay, now let's check which of the given options will give the most stable carbocation. So in the first option we have isopropyl chloride. Now when this chloride will be removed from here, what will be the carbocation that will obtain? Will get CH3, CH, CH3. Okay, this is how the isopropyl carbocation will look like, right? And we know that this is a secondary carbocation. 2-degree carbocation, that means secondary carbocation, and secondary carbocation is more stable than the primary carbocation, so this is a stable one. Okay, stable carbocation. Now it will react with the benzene ring, and as a result the alkyl group, the isopropyl group will get introduced at the ring, right? So at the ortho or para position. So this is CH, CH3, CH3. You got it? Now in the other options, that means option B and C, chlorobenzene and bromobenzene are given. So in these cases chlorine and bromine respectively will get removed. So the carbocation will be what? This benzene cation, right? But here this will not be stable. This is not stable carbocation because of the relocalized electrons. And in the last option we have chloroethene. So what is the carbocation that will get here? We have, let's write it down here, CH double bond CH. Okay, this is the carbocation. Again we know that the carbocation on the double bond is not stable. Okay, so both of them will not be stable. That means all the other options except the first one will not be stable. So only stable carbocation is the first one. So option A will be the correct answer. Question number 38 is from the chapter Organic Chemistry, Some Basic Principles and Techniques. And the question is, in which of the following molecules all atoms are coplanar? Okay, that means in the same plane. Now here we have to remember one thing, that sp2 hybridized carbon, sp2 hybridized carbon form trigonal planar structure. Okay, trigonal planar structure. That means the atoms are in the same plane. Okay, whereas if we talk about sp3 hybridized carbon, sp3 hybridized carbon form tetrahedral structure, tetrahedral structure, and we know that in tetrahedral structure more than one plane is required, more than one plane is required. So let's check. In the first option you can see the carbons are sp3 hybridized. Okay, the carbons are sp3 hybridized, that means there will be hydrogens attached like this. Okay, so more than one plane will be required, sp3 hybridization, so it will not be coplanar. Okay, not coplanar. In the second one, all the carbons seem to be sp2 hybridized, right? Is there any carbon which is sp3 hybridized? No, all carbons in the second options are sp2 hybridized. That means this structure will be coplanar. Okay, all atoms are coplanar. Let's see other options. In the third one we have sp3 hybridized carbon is present. Yes, sp3 hybridized carbons are present. so it will not be coplanar. And similarly in the last one, it seems to be very complicated molecule, but even if there is a single carbon that is sp3 hybridized, it will not be coplanar. Okay, so you can see there is sp3 hybridized carbon here. That means the only possible option is the second one. Okay, here all the carbons are sp2 hybridized, so option B will be the correct answer. Question number 39 is from the chapter Polymers, and the question is, which one of the following structures represent nylon 6,6 polymer? Okay, so we know that nylon 6,6 polymer is the polymer of adipic acid and hexamethylene diamine. Okay, hexamethylene diamine. So what is adipic acid? It is, so we have two CH2 groups here and then two carboxyl group on either sides. This is your adipic acid. And then the hexamethylene diamine means 6 CH2 groups and 2 amino groups. Okay. So this is your adipic acid and this is hexamethylene diamine. Now the resulting polymer, that is nylon 6,6, will look like this. CH2 CH2, then again C double bond O, and then this is the main bond. Okay, this is the bond part. Got it? So this is the bond formation that took place between these two molecules. Now which of the given options resemble this? In the first one we have C double bond O, then CH2 CH2, then C double bond O again, then NH. Yes, this is the same molecule. Okay, same nylon 6,6 polymer. This should be the correct one. In the second one we have no carboxyl group. This is very different. Okay, and similarly you can match all the options. The only correct match will be option number A. Okay, so this is the correct answer. Now question number 40 is from the chapter Organic Chemistry, Some Basic Principles and Techniques. And the question is, in pyrrole the electron density is maximum on. Okay, so you can see in the structure that 5 positions are marked here as 1, 2, 3, 4 and 5. Okay, now out of the 5 positions we don't have to consider the first position because it is not mentioned in the options. Okay, now position 2 and position 5 are similar, so the electron density will be same at these two positions. Okay, so electron density same on position 2 and position 5 because these two are similar positions. Similarly, electron density will be same on third and fourth carbon because these two positions are also similar. Okay, now how to determine which position will have maximum electron density? So for that we have to consider electrophilic substitution reaction. Electrophilic substitution reaction, because we know that electrophiles are electron loving groups and they will get added at the position which has maximum electron density. Okay, so this reaction, electrophilic substitution reaction, will be more favorable at the positions having maximum electron density, right? Maximum electron density. Now let's assume that the electrophilic substitution reaction takes place at third position. Okay, at 3. Then what will happen? We'll see the structures. So this is your pyrrole. 2 double bonds are there. This is nitrogen. This is hydrogen. And we know that nitrogen has a lone pair of electron. Now we are considering that the electrophile will get added at the third carbon. That means at this position. Okay. So what will happen? Electrophile has come. This is your pyrrole ring. This is nitrogen with lone pair of electron and hydrogen. This is one pi bond, and then this pi bond, the other pi bond will move at the third position at like this, okay, an electrophile will get added at this position, okay. So there will be a positive charge at this position. Now this lone pair of electron from nitrogen will move from here to here, okay. So the other resonance structure that will be formed will be like this. This is nitrogen, this is hydrogen. Now this the lone pair has moved at this position, okay. So pi bond will be here, okay. An electrophile is added at the third carbon. So these two are the resonance structures. So how many resonance structures are formed? Two resonance structures are formed. This is at position 3. At position 4 also the case will be same because these two are similar position, okay. Now let's consider that the electrophilic substitution reaction takes place at the position 2, okay. Now this is your pyrrole ring, double bonds, nitrogen with lone pair of electron, and this is hydrogen. This time at this position the electrophile has to get added, okay. So electrophile has come. Now let's see what happens. At this position electrophile has been added because this bond has moved at this position, okay. So the other bond remains at the same position, but after that there is positive charge at this position, okay, because the bond has moved from here, okay. So what will happen? Now this will try to move at this position. So the next resonance structure will be something like this. Here we have electrophile at second position and this bond has moved at this position, okay. So a positive charge now develops at this position, okay. Then lone pair will move at this position, okay. So the next resonance structure is, this is the ring, this is the electrophile, this is nitrogen, this is hydrogen. Now the lone pair has moved here, so there will be a pi bond at this position, okay, and the other pi bond was at this position, okay. So how many resonance structures this time? 3 resonance structures. 3 resonance structures. And we know that more the number of resonance structures, more is the stability, okay. So which one is more stable? In this case the compound will be most stable, okay. That means electrophilic substitution reaction will be more favorable in this case at second position. Therefore we can conclude that the electron density is maximum at second position, and since the second and fifth position are similar, so it will also be maximum on fifth position, okay. So 2 and 5, that means option A will be the correct answer. Now question number 41 is from the chapter haloalkanes and haloarenes, and the question is, which of the following compounds shall not produce propene by reaction with HBr followed by elimination or direct only elimination reaction, okay. So let's check. In the first one bromine is already present, that means there is no need for the reaction with HBr, okay, and direct elimination can be done. Elimination reaction. So this bromine and one of the hydrogens from this position will be eliminated. So minus HBr. As a result, the product that will be obtained will be a propene. Okay. CH3, CH, double bond CH2. Okay. But the question says which of them will not produce propene. So this is not the answer. Now in the second one, this is cyclopropane. So first it will react with HBr. So the bromine will get introduced here. The product will be CH3, CH2, CH2Br, okay, and after that elimination can be done. And this again bromine and one of the hydrogens from here will be eliminated, and as a result the product obtained will be a propene, okay. CH3, CH, double bond CH2. Again a propene is obtained. Now let's come to the third one. So here also HBr, reaction with HBr. So what will happen? This bromine will substitute the OH. Okay. So the product that will be obtained will be CH3, CH2, CH2Br. Okay. And then elimination can be carried out. Elimination. Again similar reaction will take place. Bromine from here and hydrogen from here will be eliminated and a propene will be obtained. Okay. double bond CH2. So in the first three reactions, first three compounds, the final product is a propene. Okay, so this is obvious that the last one will not give a propene, but still let's check. Here both the carbons are sp2 hybridized, right? Both have double bonds. So let's see what happens when it reacts with HBr. The product that will be obtained is CH2 double bond COH and Br. Okay, now this is the enol form, but its keto form is more stable, so it will undergo tautomerization. Okay, it will undergo tautomerization to give its stable form, that is keto form, and that will be CH3 C double bond O and here Br. Okay, but no further reaction will take place. This is the final product. That means no propene is obtained. Okay, no propene obtained in this case. So the correct answer will be option number D. It does not produce propene. Okay. Question number 42 is from the chapter amines, and the question is which one of the following nitro compounds does not react with nitrous acid? Okay. So in order to react with nitrous acid, the nitro compounds must have alpha hydrogen. Okay. Must have alpha hydrogen. And which of the nitro compounds have alpha hydrogen? Only primary and secondary nitro compounds. Okay, so only 1 degree, that is primary, and 2 degree, that is secondary nitro compounds can react with nitrous acid. React with nitrous acid, that is HNO2. But 3 degree cannot react with nitrous acid, HNO2. So let's check. In the first option, this is your alpha carbon and it has an alpha hydrogen attached to it. Okay, this is a this will react. Okay, this will react with nitrous acid. In the second one, again this is your alpha carbon and there are two alpha hydrogens attached, so it will also react. In the third one, this is your carbon, alpha carbon, and two alpha hydrogens are attached, so this will also react. In the last option, this is your alpha carbon and there is no alpha hydrogen attached to it. Okay, all are methyl groups, no alpha hydrogen, therefore it will not react because there is no alpha hydrogen, or we can say that it is a 3 degree nitro compound, therefore it will not react with nitrous acid. Okay, so option D will be the correct answer. Question number 43 is from the chapter Biomolecules, and the question is the central dogma of molecular genetics states that the genetic information flows from. So this is very simple question. Okay, we know that according to the central dogma, the genetic information flows from DNA to RNA and then to protein. Okay, because first DNA is replicated, right? Then DNA is transcribed into RNA. Okay, so first replication of DNA takes place, then transcription of DNA into RNA. Okay, and then translation of RNA into the protein. Okay, so this is the sequence, and therefore we can say that the correct answer will be the last one, DNA, then RNA, then protein. Option D will be the correct answer. Question number 44 is again from the chapter Biomolecules, and the question is the correct corresponding order of names of 4 aldoses with configuration given below respectively is. Okay, so if you know the structure of aldoses, you can easily answer this question. Just remember that when similar groups are on the same side, similar group on same side means the aldose will be an erythrose. Okay, it will be an erythrose. Whereas if the similar group are on opposite sides, it means the aldose will be threose. Okay. Now let's see. In the first one, we can see that OH are on the same sides, right? That means it will be an erythrose. Okay. Erythrose. Now which erythrose? D erythrose or L erythrose? So we have to consider that OH group that is at a further distance from this carbonyl CHO group. Okay. So this lower one, okay, this is on the right hand side. So this will be an D erythrose. Okay. Now the second one, here the OH groups are on the opposite side. That means it is a threose. Threose. Now the lower OH is on the right hand side, so this will be again a D-threose. Okay, right hand side. We don't have to consider that OH which is nearer to carbonyl group. We have to consider that one which is at a further distance, the lower one. Okay. Now the third one is, here we can see both the OH groups are on the left hand side, so it will be an L erythrose. Okay, both are on the same side, and on which side? Left side, so it is L erythrose. Now the last one is, here we can see both are on the opposite sides, so this is a threose, but the lower one is on the left hand side, so it is an L threose. Okay, so the correct sequence will be D erythrose, D threose, then L erythrose and L threose. Okay, so the first option we have D erythrose, then D threose, then L erythrose and L threose. Yes, this one will be the correct sequence. Okay, so option A is the correct answer here. Now question number 45 is from the chapter haloalkanes and haloarenes, and the question is, in the given reaction the product P is, okay, so the reactants are benzene and cyclohexene. These are reacting with hydrogen fluoride at 0 degrees Celsius to give the product P. Okay, now what will happen? First, this cyclohexene will react with hydrogen fluoride. Okay, so this is your cyclohexene. It will react with hydrogen fluoride. Now in hydrogen fluoride, the fluorine atom will have partial negative charge because it is more electronegative than hydrogen, and hydrogen will have a partial positive charge. This cyclobenzene, due to the presence of a pi bond, will behave as a nucleophile. Okay, so this will attack the positive hydrogen atom here in the hydrogen fluoride, and as a result what will we obtain? We'll get a product that is cyclohexane. Okay, so this will be the electrophile with a positive charge. Okay, so now the electrophile has been generated. Electrophile. Now this electrophile will react with benzene. It will react with the benzene ring, and electrophilic substitution reaction will take place. Okay, which type of reaction? Electrophilic substitution reaction, because the electrophile will get substituted here. So the final product that we'll get is this benzene ring plus the substitution of cyclohexane. Okay, like this. Okay, so two rings will get attached. So let's see which product should be the correct one. In the first option, 3 rings are there, so this is not correct. In the second option, fluorine is also there. This is also not correct. Fluorine is not there. Okay, in the last option, the correct answer is given. Okay, so option D is the correct answer. And here we complete all the questions from NEET 2016 chemistry paper of phase 2. Okay, so that's it for today. We'll be back with another session soon. Till then, keep learning, keep scoring high. For a better understanding, I would suggest you to practice same questions from our website www.examsnet.com. And for more information, download our app from the link given in the description box. Thank you so much.